I'm pleased to introduce Praveen GB from, he's the technical lead at PathPartner Technology, which is in India, but also has an office in Fremont here in Silicon Valley. Praveen went to school at Anna University, where he got both a BE and an ME degree there. And he leads the ADAS team, which I think has to do with automotive. I'm a newbie to some of these acronyms. So, Praveen, please.
Thanks for the introduction. Ladies and gentlemen, good evening. I'll be presenting my work on how we have come up with computationally efficient, embedded-friendly CNN for face recognition tasks. So, agenda as follows. So, the objective is to build a low-complex CNN for face recognition tasks. So, the face verification is an implicit part of it. So, I will introduce the problem, face verification, and what are the challenges involved to build a robust face verification system, and what are the state-of-the-art work in this domain, and then I'll compare it with my proposed method, and then I extend this to a face recognition problem, and provide our accuracy on PathPartner face recognition data set. With that, I'll be able to conclude my talk. So the problem, what face verification is. Given two images, if I can compare and then say they corresponds to the same subject or not, defines my face verification task. But to build a robust face verification task, what are the challenges involved? So these are the list of challenges: illumination variations, pose variations, and expression, occlusion, and appearance variations. So given a subject, let the illumination can be like natural or man-made, and different head pose of same subject. Irrespective of all these variations, I should be able to recognize a person. Now, to do this, typically what are the approaches involved? I can choose either non-CNN-based technique or CNN-based approach. In non-CNN-based approach, typically sparse coding and discriminant analysis-based techniques are used. But however, if we want to handle the challenges I have listed previously, I need to have additional methods, which brings in some computational overhead. So we recommend using CNN-based approaches for face recognition problem. Now, so using a CNN for face verification task, what is an objective? The feature space I learn should be invariant to pose, expression, illumination, and occlusion. That is, the kind of weights I learn for the CNN architecture should be invariant to all these variations. That is, for an intra-class variation, it should be like invariant. At the same time, for different subjects, it should be able to discriminate. To do this, to train such a CNN model, what are the components involved? Briefly, you need a good training data with multiple subjects, and for each subject, we should have multiple images with all possible variations. Also, you need a good CNN architecture suitable for this problem, and you need a good loss function to optimize the CNN model for the face recognition task. By the way, the loss function is the one which helps to optimize the CNN architecture towards this problem. Now, let me introduce some of the loss functions typically used for face recognition and face verification. Typically, softmax loss, triplet loss, and center loss are used in training a CNN for face verification task. So softmax loss. So the objective here is we try to maximize the probability of a node or a single class against n-1 class. But since we do not have an explicit signal, the models trained with softmax loss are really not effective for intra-class variations. Next one is triplet loss. So as the name suggests, we form triplets where one being an anchor image and the second one being a positive image that is from the same class as anchor, and next one is a negative image, which is from a different subject. Now, the objective of training is to reduce the distance between the anchor image and positive image and increase the distance between the anchor image and negative image by a given margin. But the key challenge here is the formation of triplets. Say I form easy triplets, the model might overfit, and it might not generalize well in the real-time scenarios. At the same time, say I form hard triplets, the model might not really converge, which is a key challenge in using triplet loss. Next one is center loss. Here, we try to define a feature vector for each class center. Now, for all images corresponding to that particular class, we try to reduce the distance between the feature vector of the class center and the feature vector of the input image. So as the name suggests, when we try to reduce the distance, or like we try to minimize the intra-class variations, since there is no explicit signal, it is not recommended to use center loss alone for training a task, for training it for face recognition. So typically, it is used in combination with other loss function. And in general, it is used in combination with softmax loss. So the final loss function is a combination of softmax loss plus center loss, which will help the CNN model for optimizing. Now, let me also introduce one more variant of convolution layers. So we are all aware of convolution layer with shared weights, where the weights are shared over space. So for problems like detection and classification, using same weights in space might do well. However, if we learn local features, that is, learning a different filter at each location, it will be really helpful in recognition kind of problems. But the key disadvantage here is, say, for example, in shared weights, say I define a filter of 3 × 3 with 10 input channels and then 20 output channels. The total parameter size will be 3 × 3 × 10 × 20. Now I bring in unshared weights. Using unshared weights, the same, say for example, I apply 16 different filters. The total parameter size will increase 16-fold. Given this statement, the limitations of using locally connected layer with unshared weights are, typically the model size will bloat up and will not be suitable for realization on embedded devices. And also, the memory bandwidth for such a trained models will be really large. And say, for example, I want to increase the depth of the network, that is adding more convolution layers, the model parameter size will further increase. So now I have introduced the loss functions, and I have given introduction to locally connected layer with unshared weights. Given these basics, I would like to give insights to the existing literature. But before that, let me introduce the data set used to benchmark face verification problem. So LFW is the data set used, labeled faces in the wild. Here, in this data set, approximately there are 5.7K people, where 2 or more images are present for 1.6K subjects, and totaling a size of 13.2K images. And for this task, we have a standard test set contains 6,000 pairs, which contains both positive and negative set. That is, 2 images corresponding to the same person as well as different person. Now, given this LFW data set, let us see what are the existing literature for this problem. So this is first set of approach, that is using unshared weights for solving face verification problem. So as you see, in all these 3 literatures, they're using locally connected layers with unshared weights, where few of them additionally uses convolution layers and fully connected layer. The first literature is deep face by Teigman et al. From Facebook. Here, the key contribution is to solve the pose, to handle the pose variations. They do apply some frontalization technique and then pass it on to the input CNN as input to CNN. And this model is trained using softmax loss. During the inference time, they have defined 2 approaches. One is weighted chi-square method, and next one is defining a fully connected layer. That is, you have a model, you add 2 more nodes that defines whether 2 images corresponds to same person or not. With this, accuracy stands on LFW stands around 97.35%. The next one is identity preserving face space by Zhu and others. So in this literature, what they have done is they define we need to define a loss function now. So we use a frontalized image with neutral expression and neutral illumination as the target image. And they try to train this network against all possible variations corresponding to same subject. Now, minimizing this L2 loss, during the inference time, along with the results for face verification, we also get a frontalized input image, which is a byproduct. So with this, the accuracy on multiply stands around 94 to 98%. And the next one is discriminative feature learning by Yandong and others. In this work, they have used softmax loss in combination with center loss during the training. And during the inference, they try to apply L2 distance over the feature vector. So with this, they're able to achieve accuracy of 99.28% on LFW. As you observe, it's not only the unshared weights technique in the last literature, it's also the usage of softmax plus center loss that has resulted in better accuracy. However, using unshared weights, as I explained previously, realization on embedded device is a key challenge. So here comes the next set of approach that is typically used for face verification, that is using, adding more layers. So in this set of work, as you observe, all of them uses minimum of 11 convolution layers. So in the first one, deep attributes by Aishwarya and others, instead of directly targeting on face verification problem, they try to learn intermediate attributes. So what they have done is they are optimizing this model for 8 attributes, where 5 are local and 3 are global. For example, male versus female, different hair color, chubby face versus skinny face. These are a set of the attributes. Once the model is trained for these attributes, during the inference time, you pass an input image over the 8 networks, and you concatenate the feature vector, and then you apply a classifier. So with this, they are able to get accuracy of 93% on LFW dataset. Next one is deep face. So in this literature, considering the challenge in using the triplet loss, they first pre-trained the model with softmax loss, and they fine-tuned the model with triplet loss. So with this, the accuracy stands 98.95%. Next one is FaceNet by Shroff and others. Here, the key contribution is they have come up with a technique to form triplets that can help in better optimization of CNN for face verification. So in this model, they have end-to-end, they use only triplet loss, and during the inference time, they apply a k-means clustering technique on the feature vector. So with this, accuracy stands on around 99.63% on LFW. Next one is FaceNet from David Sandberg. So this is our benchmark model as well. And here, they have used inception ResNet V1, and softmax plus center loss is used for training this model. With this, the accuracy stands at 99.05% on LFW. Now, however, if you want to go with approaches that are based on using 2 deep networks, the computational complexity will be an overhead. So now let us look at our benchmark model. What is the computational complexity it stands on your NVIDIA GPU? So this is our benchmark model, which is trained with softmax plus center loss, and we have validated it using LFW dataset. And accuracy stands on 99.05%. And computational complexity on your Titan X Pascal for one inference call, it takes 34 milliseconds. Now, question is it possible to bring down this complexity without degrading much on the accuracy? That's a question. So now, here comes, we introduce our network, PPFRNet, which just have 7 convolution layer and then 1 fully connected layer, where the first one is a 5x5 convolution layer, and the last 2 are 1x1 convolution layer, and rest of them are 3x3 convolution layer. And as you observe, we have defined our feature vector over a fully connected layer, which is of 256 dimension. With this, let us see where do we stand with respect to the benchmark model. So these are our results. As you observe, the benchmark model is at 99.05% with a running complexity of, like, for one inference call, 34 milliseconds. With our introduced PPFRNet, it is around 20% computationally complex compared to our benchmark model. That is 7 milliseconds of inference time for an accuracy of 91.46%. So this kind of encourages us to go ahead and extend this to a face recognition task. So what is face recognition? So you have given n images, and given a test image, if we are able to identify which it belongs to, defines our face identification or face recognition task. Again, for this problem, we can go with non-CNN-based approach. However, if you go with non-CNN-based approach, for the face recognition task, we are supposed to store the representation. That is, since in the non-CNN approach, it needs multiple images per subject during the registration phase. And also, to store the representation, we would end up using larger memory. And scalability becomes a question by going ahead with non-CNN approach. So we recommend using CNN-based approach for face recognition task as well. So let us look at how it is during the registration phase. To register, we have a fully trained CNN model, and we pass one image, and we get a unique feature vector. Now, we repeat the same for each image that is getting registered into our system, and we get n different unique feature vectors. So during the testing phase, we have a face plus landmark detector that gives me a tight crop of the face, which will be an input to CNN feature extractor. And further, I also have the feature vector that are generated during the registration phase. So given this, I'll be able to classify and define which subject it belongs to. Now, we want to profile this model on the publicly available data sets. But as we observe, we do not see any data set that can clearly demark between illumination variation, pose variation, expression, and occlusion. So that's why we have come up with our own data set, PathPartner face recognition data set. In this data set, we cover all possible variations, that is pose variation, illumination, expression, and occlusion. And this data set is captured for a total duration of 10 days with 15 male and 7 female. And as you observe, for illumination, what we have done is we have defined 3 cases. That is, we fix the pose, and then we try to move the light source from one point to other point. And in the second case, we keep the light source constant, but we switch between them. And then in the last one, we define a constant source. Now, let us look at what do we really need to register a person into our data set or into our system. Yeah, so this is our registration data. All we need is one single image of a person who wants to get registered with neutral pose, that is frontal pose, neutral illumination, and neutral expression. So once we register, how do it look like? So this is our test set. We have defined 3 test sets. In test set 1, as you observe, we are controlling the pose, and at the same time, we are trying to change the illumination from left to right. In test set 2, again, we have a controlled pose, but we are switching the illuminations between the constant sources. And in test set 3, we have kept the illumination constant, but we want to see how our algorithm responds to different pose variation, different expression, and different occlusion. And for this experimentation, we have registered 13 people into our data set, and 9 we have not registered. So that being our test set. Now, let me show you some of the samples from this test set. So in test set 1, as you observe, the light source switches from left to right. And these are some of the samples from test set 2 and test set 3. Now, let us look at the accuracy. So before I go ahead with giving my accuracy numbers, let me also define some of the terms I have used here. So that is positive recall accuracy and negative recall accuracy. So we have some set of ground truth images which are negative, that are not registered into our data set. And I define my positive images as the one that are registered into our system. So in the positive recall accuracy, what we try to define is we want to minimize, if we have 0 false negatives, that results in 100% positive recall accuracy. Similarly, for a negative recall accuracy, what we are expecting is if a person is not registered, he should not be detected as someone else, that being 0 false positives. So given these terms, our benchmark model, as you observe, what we have done, we have fixed the negative recall accuracy around 98%. And what we are trying to see is, compared to our benchmark model, we are trying to see how the positive recall accuracy varies. So as you observe, there is a deviation of roughly 5% compared to our benchmark model. But at the same time, we are able to do this task at 20% computational complexity compared to our benchmark model. Now, let us also look the numbers on some of the embedded platforms. So we have profiled this architecture on TX2 as well as on Qualcomm Snapdragon 820 GPU. So for one inference call on TX2, it takes 7 milliseconds, And for one inference call on 820 GPU, it takes 22 milliseconds. Now, question is, if I extend this problem for a video-based face recognition, if I perform face recognition, if I call the CNN for every single frame, the computational complexity will be multifold. So how do we handle this problem? So here comes our next contribution, that is face recognition tracker. Let's go into the block diagram. So typically, what we have is we have a face detector plus landmark detector. We have a CNN feature extractor followed by a classifier. So given face recognition tracker, what we do is we call the CNN inference engine for a duration of n frames. And in our case, it is typically 1 second for 30 frames. And say we are having a recognition result, right? We pass this control will be switched to the face recognition tracker. Now, question is, once the control passed to face recognition tracker, when do we reset? When do we give the control back to CNN again to determine which subject it belongs to? So these are set of the conditions. That is, say if face is not detected in the previous frame, or suddenly one guy covers his face and suddenly one guy pops up, right? And in the third condition is if we see a drastic switch in the scale in which face is getting detected, under these conditions, we identify, OK, there is a switch between the subjects. So we pass the control back from face recognition tracker to the CNN inference engine. With this, let us look where our accuracy number stands. So by introducing the face recognition tracker, we are able to come up with a stable face recognition solution. So as you observe, by enabling tracker, there is an improvement of 2% over the PPFR net. Now let us also look at the computational numbers. So typically, if we call CNN engine for 30 frames on TX2, it takes 198 milliseconds. And on 820 GPU, it takes 660 milliseconds. Now, by introducing this tracker, with the kind of confidence score we get, we will be able to early terminate the CNN call by roughly between 50 to 75%. Given that we will not be calling CNN engine again and again for each frame, that brings the computational complexity on TX2 from 198 milliseconds to 66 to 99 milliseconds. And on 820 GPU, from 660 milliseconds to roughly to 220 to 330 milliseconds for a typical use case. So with this, it is very evident that we do not really need a deep network for a face recognition problem. And at the same time, we do not need a variant of convolution, that is using features such as unshared weights. So with this, I conclude my talk by summarizing, with right combination of training data and cost function, a low complex CNN models are sufficient for face recognition tasks. And we recommend using face recognition tracker to not only to achieve a stable results, and it also helps in bringing down the computational complexity. And these are the references. Let me take a minute to describe about PathPartner. At PathPartner, we are a design engineering services company. We are founded in 2006, headquartered in Bangalore. Our current company strength is roughly 280, where 10% of workforce is with R&D domain. We also have quality certifications, ISO 9001 2015 and ISO 27001 2013. We have our R&D centers in Bangalore and in Fremont, California, and also we have our global marketing presence. We are also a member of Embedded Vision Alliance, and we are partner of various semiconductor companies. We work from algorithm and optimization to putting it onto embedded system, optimization, right to applications. So these are our key skill set. If you are interested, you can contact these email IDs. Now, any questions?
Thank you, Praveen. I had a practical question. You targeted both the NVIDIA as well as the Snapdragon chip. NVIDIA, presumably you used CUDA, or did you use OpenCL or some other?
So we have used CUDA for this profiling.
OK.
Yeah.
And so the CUDA code is not directly converted from C, I think. So you probably use just standard C or C++ for the Snapdragon chip?
Yeah, so on NVIDIA GPUs, so they have given a set of tools. So all we need to define is we need to give a fully trained CNN model using trained with Caffe. So given that, we'll be able to profile where it stands on a TX2 GPU.
Okay. Yeah, I'm mainly trying to figure out that 7 milliseconds versus the 22 milliseconds. How much of that was due to different software environments versus kind of just different performance?
So ideally, the environment might not really matter. I guess it depends on the number of CUDA cores we use for this particular task. So either it is, if the model is trained with Caffe or TensorFlow, end of the day, we get the model coefficients. So the kind of environment we use might not really matter.
Okay. Other questions from the audience? All right. Well, thank you for attending. Thank you, Praveen, for your talk.